Picture yourself standing on a stone arch bridge, feeling the cool breeze off the river below, your hands resting on weather-worn parapets that have stood for centuries. This isn't just any bridge. This structure was built 800 years ago by medieval artisans who never saw a computer, never used reinforced concrete, and yet created something so durable it has survived earthquakes that flattened modern buildings. There's something almost magical about these ancient crossings, something that speaks to a deeper understanding of the natural world that we're only now beginning to fully appreciate. These bridges weren't just built to cross rivers, they were built to endure, to become permanent fixtures in the landscape, silent witnesses to centuries of human history. What's truly astonishing is that these medieval builders achieved what many modern engineers would consider nearly impossible. Without seismographs or advanced mathematics, they designed structures that could absorb and dissipate the incredible forces of earthquakes, forces we can now measure with precision but still struggle to fully control. They worked with stone, timber, and simple mortar, yet their creations have outlasted countless newer bridges made with steel and concrete. There's a profound lesson here about human ingenuity, about how observation, intuition, and respect for materials can sometimes outperform even the most advanced technology. These builders looked at how trees sway in the wind, how water flows around obstacles, how stones settle over time, and they incorporated these natural principles into their designs. Today, we're going to unravel the secrets behind these remarkable structures. We'll explore how 13th century bridge builders across Europe and Asia developed techniques that modern engineers would later rediscover and formalize. From flexible joints that allow movement during tremors to foundation, designs that stabilize against shifting ground, these artisans were centuries ahead of their time. We'll see how their understanding of geometry, materials, and environmental forces created bridges that aren't just historical curiosities, they're living lessons in resilience that remain relevant in our earthquake-prone world. This is a journey into the mind of medieval engineers, a chance to appreciate how their wisdom can inform our future, and an opportunity to stand in awe of what human hands and minds can achieve when they work in harmony with nature rather than against it. To truly grasp the brilliance of these medieval bridges, we need to step into the world that created them. The 13th century was not some dark, stagnant period. It was a time of vibrant expansion and connection. Trade routes were the internet of their day, buzzing with merchants, pilgrims, and ideas moving between growing cities and powerful kingdoms. From the Silk Road weaving across Asia to the bustling merchant networks of Europe, this flow of people and goods created an urgent need for reliable infrastructure. Bridges became the critical nodes in this emerging network, and building them was one of the most ambitious and respected endeavors of the age. This wasn't just about getting across a river. It was about fueling economic growth and uniting communities. The master builders behind these projects operated without blueprints in the modern sense. They were artisans, part of tight-knit guilds that guarded and passed down trade secrets through a long system of apprenticeship. A young man would spend years learning the craft, not from books, but by mixing mortars, shaping stones, and observing how structures behaved under load. Their knowledge was a living, breathing thing, built on generations of hands-on experience and careful observation. They understood geometry not as abstract theory, but as a practical tool, using compasses and ropes to lay out perfect arches that could channel immense weight down into the earth. Every single bridge was a custom solution, a direct response to the specific challenges of its site, the width of the river, the type of soil, the available local stone, and the known risks of floods or earthquakes. This last point is crucial. This era was not seismically quiet. Historical records tell us that regions from the Italian peninsula to parts of China experienced significant and frequent earthquakes. For the builders in these areas, seismic resilience wasn't an abstract concept. It was a matter of life, death, and economic survival. A collapsed bridge could cut a city off from trade and aid. So they learned by watching. They saw which structures fell and which ones stood. They noticed that rigid, inflexible constructions were the first to fail, while those that could absorb and move with the energy of a tremor had a fighting chance. This relentless environmental pressure forced them to innovate, to think beyond mere function and design for outright survival. They were essentially conducting a centuries-long, real-world experiment in structural engineering, and the results of that experiment are still standing for us to study today. Now consider the constant, looming threat that shaped their work. Earthquakes were not just occasional disasters to these medieval builders, they were powerful teachers. In regions like Italy, Anatolia, and parts of China, the ground shook with a frequency that forced a profound shift in thinking. These artisans had no way to predict when the next tremor would strike, but they became brilliant students of its effects. After a quake, they would carefully examine the damage, noting which buildings collapsed and, more importantly, which ones remained standing. They saw that rigid, inflexible structures often shattered under the stress, while those with some give, some ability to sway and move, had a much better chance of survival. This hands-on learning process led to some ingenious adaptations. Builders began intentionally designing structures that could dance with the earthquake rather than fight against it. They might leave small gaps between stones or use softer mortar mixes that allowed for slight shifting without catastrophic failure. The concept was all about distributing and dissipating energy, letting the violent forces of the quake travel through the structure in a way that minimized damage. It was a brilliant, intuitive grasp of what modern engineers now call ductility. They understood that trying to make something completely immovable was a losing battle against nature's immense power. The real secret was learning how to bend without breaking. This pragmatic approach transformed bridge design. Builders started incorporating features that enhanced flexibility. They might use slightly tapered stones in arches so they could settle back into place after movement, or build piers with broader bases to resist tipping. Every earthquake became a brutal but effective test, providing new data that was incorporated into the collective knowledge of the guilds. This wasn't theoretical engineering. It was a survival skill, refined through generations of observation and incremental improvement. The resilience we see in these ancient structures isn't accidental. It's the direct result of centuries of learning from the Earth's violent movements and adapting with remarkable creativity. But the true genius of these builders wasn't just in choosing the right materials. It was in understanding how to make them work together in harmony. They treated stone, mortar, and timber not as separate components, but as a unified system, each element compensating for the other's weaknesses. A stone arch, for instance, is incredibly strong under compression, but it has almost no tensile strength. It can't stretch or bend without cracking. The mortar joints, however, provided just enough give to absorb tiny movements, acting like microscopic shock absorbers. And in some brilliant composite designs, builders would incorporate timber beams within the stonework, creating a skeleton that could flex and sway during a tremor, much like a tree in a storm. This holistic approach to material science meant that the entire structure behaved in a coordinated way under stress, distributing forces along multiple pathways so that no single point had to bear the full brunt of an earthquake's energy. It was a symphony of materials, each playing its part, orchestrated by masters who understood that resilience is found not in fighting nature's forces, but in gracefully yielding to them. Now, one of the most brilliant adaptations to emerge from this era was a seemingly simple change in shape that revolutionized structural stability: the pointed arch. If you look at ancient Roman bridges, you'll see they're dominated by the classic semicircular arch, a design that's incredibly strong but has one major weakness: it pushes outward with tremendous force. All that weight from the top of the arch wants to splay the supporting piers apart, a phenomenon known as lateral thrust. In an earthquake, this outward pressure becomes a catastrophic liability, as shaking ground can easily topple piers that are already fighting to stay upright against this constant sideways force. The pointed Gothic arch, by contrast, is a masterpiece of physics. Its elegant peak acts like a funnel, channeling the immense weight of the bridge and its load more directly downward into the foundations. This dramatic reduction in lateral thrust meant the supporting piers could be built slimmer and taller, requiring less massive, bulky stonework to counteract that outward push. But the seismic benefits went even deeper. In a tremor, a lighter, more slender structure has less mass wanting to move, and it can oscillate and flex without building up destructive resonant frequencies. Think of it like a tall, young tree swaying in a storm versus a rigid, old one that snaps. The pointed arch allowed the entire bridge to become a more dynamic, responsive system. A perfect example of this innovation in action is the world-famous Pont Vecchio in Florence, Italy. While the bridge we see today was rebuilt after a flood in the 1400s, it stands on the site of an earlier medieval bridge and embodies the design principles honed over centuries. Its series of elegant pointed arches don't just create a beautiful profile over the Arno River, they form an incredibly resilient skeleton. The forces from each arch are channeled precisely where they need to go, and the structure as a whole can absorb the energy of ground movement, flexing minutely at the joints and then settling back into place. This is the genius of the medieval mind. They didn't just see an arch as a shape, but as a carefully calibrated tool for directing force, a tool that turned a vulnerable structure into a lasting monument. Of course, everything we've discussed about arches and flexible materials would be meaningless if the entire structure was built on shaky ground. This brings us to what might be the single most critical element of medieval seismic design: the foundation. These builders possessed a profound, almost instinctual understanding that a bridge is only as strong as what lies beneath it. They knew that the violent energy of an earthquake doesn't just travel through the air, it pulses upward from the very earth itself. If the foundation was weak or unstable, that energy would find its way into the structure with devastating consequences, turning even the most beautifully engineered arch into a pile of rubble. Their approach was one of meticulous, painstaking preparation. Before a single stone was laid for the piers, teams of laborers would begin the arduous task of excavation. In ideal conditions, they would dig straight down until they hit the unyielding surface of bedrock, effectively anchoring their bridge directly to the most stable part of the Earth's crust. This created a direct, solid connection that minimized differential movement between the ground and the structure during a tremor. But what did they do when the riverbed was soft, composed of silt, sand, or loose gravel that could liquefy under seismic pressure? They couldn't just give up. Their solution was ingenious, driving long, sturdy piles deep into the earth. These were essentially giant wooden stakes, often made from water-resistant oak or elm, hammered down until they reached a compact, stable layer of soil far below the surface. It was a process that required immense effort and patience, but it created an artificial bedrock, a firm platform upon which they could build with confidence. And they didn't stop there. On top of these piles or the excavated bedrock, they would often construct what's known as a grillage, a massive platform of interlocked timber beams forming a giant crib. This wooden cage would then be filled with rubble, stones, and hard-packed earth, creating a wide, heavy, and incredibly stable base that distributed the immense weight of the bridge evenly across the ground below. In earthquake zones, they took this concept even further, widening and deepening these foundations to an almost over-engineered degree. This wasn't wasteful, it was wisdom. A broader base dramatically increased resistance to the overturning forces of a quake, acting like the wide, flat bottom of a ship that keeps it upright in a storm. This entire process of rooting the structure was their way of ensuring that when the earth shook, the bridge would move as one solid, unified mass. Instead of having different parts shifting and grinding against each other at different rates, a sure recipe for fractures and collapse, the entire edifice would tilt, sway, or settle slightly, but remain intact. It was a masterful grasp of soil-structure interaction, a complex principle modern engineers would only begin to formalize with mathematical models centuries later. This intuitive understanding of movement brings us to one of the most brilliant and subtle innovations in medieval seismic design, the deliberate incorporation of flexibility. Rather than striving for a perfectly rigid, monolithic structure, a goal that would ultimately prove futile against the Earth's raw power, these builders intentionally introduced points of controlled movement. They understood that a bridge needed to breathe, to sway, and to settle, and they designed it to do so without compromising its integrity. It was a philosophy of working with nature's forces, not against them, and it manifested in the clever use of joints and gaps that acted as built-in shock absorbers. Throughout the stonework, particularly at the most critical stress points, masons would leave intentional gaps between the massive blocks. But these weren't just empty spaces, they were carefully filled with pliable, forgiving materials. One common filler was oakum, which is essentially hemp fiber soaked in tar. This created a dense, fibrous pad that could compress and expand, absorbing energy without crumbling. In more elaborate and important bridges, they might use strips of lead, a malleable metal that could deform under pressure and then rebound, effectively sealing the joint again after the movement had passed. During an earthquake, these flexible joints became the structure's secret weapon. As the ground shook and tried to force the stone blocks to grind against each other, the pliable filling took the strain. It allowed for that tiny, crucial amount of slippage and shift that prevented stress from building up to a catastrophic level. Without these joints, the immense forces would have nowhere to go except into creating massive cracks, but with them, the energy was harmlessly dissipated as friction within the joint itself. The sophistication didn't end there. The very stones of the arches, known as voussoirs, were often shaped with incredible precision to enhance this self-stabilizing behavior. In some bridges, these wedge-shaped stones were cut with a very slight taper or were set with intentionally asymmetric mortar joints. This might have looked like a minor imperfection to the untrained eye, but it was a calculated masterstroke. This subtle shaping created a kind of mechanical memory within the arch. After being jolted out of position by seismic shaking, the inherent angles and weight distribution of the stones would encourage the entire arch to settle back towards its original, optimal form. It was a passive self-centering system, engineered centuries before we had a term for it. The arch literally knew how to put itself back together. This entire approach was a profound form of biomimicry, though they would never have called it that. The builders were mimicking the behavior they observed in the natural world all around them. They saw how a grove of trees could withstand a ferocious windstorm by swaying and bending, their roots allowing minute movements while their flexible trunks absorbed the energy. They saw how riverbanks were lined with resilient, yielding reeds that bounced back after a flood. Unlike rigid structures that were washed away, their bridges were designed with that same organic resilience. They weren't trying to create immutable monuments of stone. They were creating structures that lived and moved with the land, that had a kind of engineered vitality. This medieval principle of allowing for movement is so fundamental that it remains a cornerstone of all modern seismic design. The expansion joints we see on every contemporary bridge and skyscraper, those metal teeth that allow sections to slide independently, are the direct descendants of the lead-filled gaps and oakum cushions used by masons 800 years ago. Now, to see these principles in breathtaking action, we journey to Japan and the magnificent Kintakeo Bridge. While its current form dates to the 17th century, this iconic structure is a living museum of seismic design, thinking that was perfected over the preceding 400 years. It stands as a powerful testament to a philosophy where destruction is not an end, but a brutal yet effective teacher. The bridge's history is one of repeated loss and resilient rebirth, with each reconstruction absorbing the hard lessons of the past to create something even stronger, embodying a truly adaptive and living tradition of engineering. The most visually stunning feature of Kintakeo is its series of 5 graceful wooden arches soaring over the Nishiki River. At first glance, they appear impossibly delicate, a work of art rather than a feat of structural strength. But their beauty is deeply functional. Unlike a rigid stone arch, these wooden curves are designed to flex and breathe. During an earthquake, the entire structure is meant to sway and deform, absorbing the seismic energy through the natural elasticity of the timber itself. The wood's fibrous structure allows it to bend significantly without snapping, much like a bamboo stalk in a typhoon. This flexibility is the bridge's primary defense, allowing it to move with the earth rather than resist it to the point of fracture. The method of construction is where the medieval genius truly shines. The entire arch system is built using an intricate, interlocking joinery technique, masterfully carved without a single metal nail or bolt. This is a hallmark of traditional Japanese carpentry known as miyadeku. Each joint is a complex puzzle piece, precisely cut to fit with its neighbors under immense pressure. In a seismic event, these joints are the key to the bridge's survival. They allow for controlled movement and shifting along predefined pathways. The timbers can slide and adjust within the confines of the joinery, dissipating energy through friction. Then, like a perfectly tuned spring, the inherent tension and geometry of the interlocked system encourages the entire arch to rebound, to settle back towards its original, elegant form. It is a masterpiece of passive energy dissipation. This wooden marvel, however, rests upon a foundation that tackles the other great threat, water. The stone piers are monumental works in their own right, and their design directly addresses a secondary seismic danger known as liquefaction scour. During a major earthquake, saturated soil can temporarily behave like a liquid, a process called liquefaction. Meanwhile, the quake's shaking can also trigger powerful waves and currents in the river, which then scour and erode the soil around the bridge's foundations, undermining their stability. The builders of Kintakeo countered this with brilliantly designed cutwaters. These are the triangular, knife-edged extensions on the upstream side of each pier. They don't just slice through the current to reduce drag. During a flood or a seismic event, they actively defend the pier. By breaking the force of the water and directing the flows smoothly around the base, they prevent the turbulent erosion that could wash away the supporting soil and leave the piers dangerously exposed and vulnerable to collapse. This holistic design protects the bridge from a double threat, the shaking from below and the scouring from the sides. perhaps the most profound lesson from Kintakeo is not found in a single design feature, but in its entire history. This bridge has fallen down multiple times. It was destroyed by floods in 1673 and again in 1950 after centuries of standing. But each time, the community did not see it as a failure of the original designers. Instead, they treated it as a learning opportunity. The rebuilding process became a ritual of improvement. After each collapse, engineers would meticulously study the wreckage to identify the exact point of failure. Was it a specific joint that gave way? Did the scour undermine a particular pier? This forensic analysis then directly informed the new design. The 1950 reconstruction, for instance, likely incorporated deeper foundations and even more robust joinery based on the lessons of the previous failure. This iterative process, build, test, fail, learn, and rebuild better, is the very essence of resilient design. It proves that longevity isn't about creating something that never falls, but about building a society that always learns and always has the will to rebuild with wisdom. Kintakeo is not a static relic. It is a dialogue between human ingenuity and the irresistible forces of nature, a conversation that continues to this very day. While the wooden marvels of Japan showcase flexibility, the stone bridges of Europe tell a different but equally compelling story of resilience. Crossing the great rivers of France and Spain, structures like the Pont d'Avignon and the Puente Romano in Merida stand as monuments to a pragmatic, no-nonsense approach to seismic design. These builders worked with the heaviest of materials, massive blocks of limestone and granite, yet their true genius lay in how they orchestrated this weight and mass to work dynamically against the forces of an earthquake. Unlike the light, flexible wooden arches of the East, European bridges often employed a strategy of controlled rigidity and brute strength, but applied with a surprising level of sophistication and adaptability to local conditions. One of the most effective secrets in their design was the intentional use of irregularity. To the modern eye, a bridge with arches of different widths and piers of varying thickness might look haphazard, even unsightly. But this asymmetry was a calculated masterstroke. Medieval engineers were brilliant site-specific designers. They would carefully survey the riverbed, noting where the current ran fastest and where the underlying soil was softest. The piers in deeper water or softer sediment were built thicker and more massive to provide a sturdier anchor point and resist scouring. The arches they supported might be made slightly narrower to reduce the span and the load. Conversely, over firmer ground or shallower water, the piers could be slimmer and the arches wider. This custom-tailored approach created a structure that was perfectly balanced for its unique location. During seismic shaking, this irregular massing prevented the entire bridge from oscillating in a uniform, synchronized wave, a phenomenon that can amplify forces and lead to catastrophic failure. Instead, different sections would move at slightly different frequencies, effectively canceling out and dissipating the energy across the entire structure. But the real hidden weapon of these European bridges was what lay inside their spandrel walls, the solid walls between the top of the arch and the roadway above. These weren't just empty spaces, they were packed tight with a chaotic mix of rubble, stone chips, and mortar. This loose fill material, known as implekton in ancient Greek construction, served a critical dual purpose. First, it added immense weight, lowering the bridge's center of gravity and making it much more stable and resistant to overturning, much like a weaver's loom stands firm because of its heavy base. Second, and more ingeniously, this rubble filling acted as a primitive but highly effective damping system. As the bridge vibrated during an earthquake, the thousands of pieces of loose rubble would shift, grind, and settle against each other. This constant internal friction converted the kinetic energy of the vibration into harmless heat and sound energy, dramatically reducing the amplitude of the oscillations. It was the medieval equivalent of the mass dampers we install in modern skyscrapers today, a way to absorb and neutralize destructive motion from within. This philosophy of tolerating deformation was the cornerstone of their success. These stone giants were not designed to be perfectly rigid. The master builders understood that stone, while strong in compression, is brittle and will crack if forced to bend. So they designed their structures to handle settlement and movement. The mortar joints, often made with lime-based mixes that remained slightly flexible for years, allowed for minute adjustments. The sheer weight of the structure meant that any movement was usually slow and gradual, allowing the arches to settle into a new, still stable equilibrium. This stands in stark contrast to many 20th century bridges built with rigid, reinforced concrete and steel. When faced with unexpected ground movement or seismic loads they weren't designed for, these modern structures, lacking the ability to deform even slightly, often failed catastrophically by snapping at their weakest points. The enduring lesson from these medieval masons is a humbling one for modern engineering. Sometimes the key to survival isn't absolute strength, but a calculated ability to yield. Beneath the apparent artistry of these medieval bridges lies a hidden language of numbers and shapes, a rigorous geometric code that governed every curve and proportion. This wasn't mere decoration, it was the very heart of their structural logic. Master builders operated from a profound belief that the universe itself was constructed on geometric principles, and by mirroring these perfect, divine ratios in their work, they were tapping into a fundamental source of stability and harmony. They saw a direct connection between mathematical beauty and physical strength, an idea that modern engineering is only now beginning to quantify with advanced computer modeling. The tools of this trade were elegantly simple yet incredibly powerful: the compass for drawing perfect circles and arcs, and the straightedge for defining true lines. With these two instruments, a master could lay out an entire bridge plan directly on a tracing floor, a large, flat surface of plaster or stone where full-scale designs were chalked out. This process allowed them to visualize the flow of forces through the structure before a single stone was quarried. When they drew an arch, they weren't just sketching a pretty curve, they were carefully plotting the path that immense weight would travel from the deck down to the foundations. The specific radius of the arch, determined by the fixed pivot of the compass, directly influenced how much lateral thrust it would generate. A steeper, more pointed arch, created by using two compass centers, naturally funneled that force more vertically, reducing the burden on the piers. This precise control over form was their primary method of engineering resilience. Among these geometric rules, the golden ratio, approximately 1.618 to 1, held a special place. This proportion, found in everything from seashells to the human body, was believed to possess an innate aesthetic and structural balance. Builders would use it to determine the ideal relationship between an arch's height and its span, or the width of a pier to its height. A pier sized according to this ratio wasn't just pleasing to the eye, it was optimally proportioned to resist buckling under compressive loads. Similarly, an arch with a rise-to-span ratio based on the golden section would experience more uniform stress distribution, minimizing points of concentrated pressure that could lead to cracking during an earthquake. This wasn't blind faith in a magic number, it was the result of centuries of observational experience. They had empirically discovered that structures built to these proportions simply performed better and lasted longer. Symmetry was another cornerstone of their geometric doctrine, but it was a practical, load-bearing symmetry. A perfectly symmetrical bridge with identical arches and evenly spaced piers ensures that weight and force are distributed equally across every support. This prevents any single element from being overloaded, creating a balanced system where all components work in concert. When seismic forces hit, this balanced design helps the entire structure resist twisting or racking motions that are particularly destructive. The energy of the quake is spread throughout the network of arches and piers rather than being focused on a single weak point. This principle of redundant load paths is a bedrock of modern seismic design. If one element fails, others can pick up the slack. Medieval builders arrived at this conclusion not through calculus, but through an intuitive understanding of balance and the observable behavior of their creations. Perhaps the most astonishing aspect of this geometric mastery is how it foreshadowed our most advanced engineering software. Today, engineers use finite element analysis, or FEA, to create complex digital models of structures. They break a design down into thousands, even millions, of tiny geometric elements to simulate how stresses will flow through it under various loads, identifying high-pressure points before construction even begins. Medieval builders were doing a rudimentary, full-scale version of this right on their tracing floors. Their compass-drawn curves were a way of optimizing load paths. Their proportional rules were algorithms for minimizing stress concentrations. Their symmetrical layouts were a method for ensuring even force distribution. They were, in essence, performing analog computations with string and chalk, achieving a level of predictive design that would not be formally equaled for centuries. The enduring lesson from their drafting tables is a powerful one. True resilience often emerges from the elegant application of fundamental principles, proving that the most sophisticated solutions can sometimes be drawn with the simplest of tools. While the graceful arches and sturdy piers formed the visible strength of a medieval bridge, some of the most brilliant design thinking was dedicated to managing an invisible and often overlooked danger: water. It wasn't enough to simply withstand the direct shaking of an earthquake. These structures also had to survive the devastating secondary effects that a tremor could unleash. A quake could instantly transform a placid river into a raging torrent, sending powerful waves and debris slamming into the bridge's supports. Even more insidiously, the violent shaking could liquefy the water-saturated soil around the foundations, turning solid ground into a shifting, unstable slurry that could swallow entire piers. Medieval builders recognized this dual threat with remarkable clarity, and their response was a masterclass in holistic, multi-hazard design that protected the structure from every angle. The most iconic feature born from this understanding is the cutwater. Those elegant, triangular extensions on the upstream side of bridge piers are far more than decorative flourishes. They are precision instruments for managing hydraulic force. Imagine the immense pressure of a flood current, filled with swirling logs and other debris, slamming directly into a flat-faced pier. The impact would be tremendous, and the turbulence created on the downstream side would endlessly scour and erode the soil from around the pier's base, undermining its stability. The cutwater's sharp, angular profile solves both problems in one brilliant stroke. It functions like the bow of a ship, cleanly slicing the current in two and deflecting water and debris smoothly around the sides of the pier. This dramatically reduces the direct impact force and, just as importantly, minimizes the destructive vortex of water that would otherwise dig a cavernous hole around the foundation. During an earthquake, this same feature becomes a critical structural reinforcement. The cutwater's mass and triangular shape act as a giant buttress, greatly increasing the pier's resistance to the powerful lateral or sideways forces generated by seismic shaking. It's a perfect example of a single, elegant solution addressing multiple, complex problems simultaneously. Beyond reinforcing the piers, builders also manipulated the very form of the bridge to outsmart floodwaters. In regions prone to seasonal flooding, they would often raise the height of the arches significantly, lifting the entire roadway high above the typical water level. This design choice had a profound seismic benefit that went beyond just avoiding flood damage. By elevating the arches, builders were effectively reducing the overall mass of the superstructure, the part of the bridge that sits atop the piers and is most vulnerable to shaking. Less mass high up means less inertial force acting like a pendulum during an earthquake, making the entire structure more stable and less likely to experience catastrophic whiplashing effects. This principle of mass reduction at height is a key tenet of modern seismic codes for skyscrapers, yet medieval engineers arrived at it through practical necessity and observational wisdom. Perhaps their most advanced insight, however, was into the behavior of the earth itself. Without any knowledge of modern soil mechanics, they understood through experience that ground which was saturated with water became dangerously unstable during a quake. They observed that structures built on muddy riverbanks often fared worse than those on drier, firmer ground. Their solution was twofold: depth and drainage. Foundations were dug down relentlessly until they reached a compact, reliable stratum, bypassing the unstable, waterlogged layers near the surface, but they didn't stop there. Evidence from archaeological excavations shows that many medieval builders incorporated primitive but effective drainage systems around their foundations. They would surround the stonework with layers of loose gravel and rubble. This porous material acted as a French drain, providing a pathway for groundwater to seep away from the critical foundation elements, thus keeping the surrounding soil drier and more stable. By preventing water from pooling around the base, they drastically reduced the risk of soil liquefaction, that terrifying phenomenon where solid ground temporarily turns into a quicksand like fluid under seismic stress. This comprehensive approach, considering everything from the flow of the river to the saturation of the soil, reveals a systems thinking mindset that is the true hallmark of engineering genius, creating structures that were resilient not just to one threat, but to the entire chaotic symphony of nature's forces. This relentless process of learning from failure was the engine of medieval engineering innovation, a slow but profoundly effective form of research and development conducted not in laboratories but in the real world. Without textbooks on structural dynamics or computer models to simulate stress, these master builders relied on the most unforgiving teacher of all: collapse. When a bridge fell, it wasn't seen as a final defeat but as a costly yet invaluable lesson. The community would mourn the loss, but the artisans would immediately descend on the wreckage, not to clear it away, but to study it with the meticulous focus of a detective at a crime scene. Their goal was to perform a kind of proto-forensic engineering, piecing together the sequence of failure from the broken stones and splintered timber. They looked for the telltale signs that revealed the structure's breaking point. Did the piers lean in a particular direction, suggesting the foundation had shifted unevenly in the soft riverbed soil? Perhaps the mortar had crumbled at the crown of the arch, indicating a fatal weakness under tension. Maybe the spandrel walls had bulged outward, showing that the rubble fill inside had not been sufficient to dampen the vibrational energy. Each crack, each tilted stone was a clue. This careful observation allowed them to move beyond guesswork. They could pinpoint the exact mechanism of failure, transforming a disaster into a dataset. The solution then became a targeted adjustment to their design vocabulary. If the piers had tipped, they might be made broader and founded deeper on a timber grillage. If an arch had cracked, perhaps the next one would be a slightly more pointed Gothic shape to better channel the forces downward. This was knowledge written in stone and paid for with immense effort, a continuous cycle of hypothesis, testing, and refinement played out over generations. The true power of this empirical method lay in its collective and cumulative nature. A single master builder might only witness a handful of major collapses in his lifetime. But through the guild system, the hard-won lessons from dozens of failures across entire regions and centuries were gathered, filtered, and preserved. This created a living library of best practices, a slowly evolving standard of care that was passed down orally and through practical demonstration from master to apprentice. A young stonemason wouldn't just learn how to shape a stone. He would learn why a certain type of stone was chosen for a pier, or why the mortar mix for a specific joint included horsehair for flexibility. He was inheriting the condensed wisdom of countless past failures, each one preventing a future catastrophe. This was evidence-based engineering in its purest form, where the evidence was written in the rubble of fallen bridges and the success was measured in centuries of service. It was a system built on deep respect for the materials, the forces of nature, and the responsibility these artisans felt towards the communities that depended on their work for safety and connection. To fully appreciate why medieval builders invested such incredible effort into durability, we must look beyond pure engineering and into the very soul of the societies that commissioned them. A bridge was never just a utilitarian crossing. It was a profound symbol, deeply woven into the cultural and spiritual fabric of the community. It represented a sacred link, a connection not only between two riverbanks but between the earthly and the divine, the mortal and the eternal, the known and the unknown. This symbolic weight transformed construction from a mere civic project into a spiritual act, an offering of craftsmanship meant to honor higher powers and stand for generations as a testament to faith and community. This mindset was perhaps the most powerful, if intangible, ingredient in the recipe for their legendary resilience. In the Christian world of medieval Europe, this spiritual connection was made manifest in stone and ritual. It was common for important bridges to incorporate small chapels or oratories directly into their structure. The famous Pont Vecchio in Florence originally had a chapel dedicated to St. John the Baptist, while London Bridge famously supported a magnificent chapel dedicated to Thomas Becket. These were not afterthoughts, they were integral to the bridge's identity. Travelers, before embarking on a perilous journey, would stop to pray for safe passage. Merchants would give thanks for a successful crossing. These spaces required priests and constant upkeep, ensuring the bridge itself was perpetually watched over and maintained. The presence of the sacred literally sanctified the structure, making its collapse not just a structural failure but a spiritual one. This created a powerful, self-perpetuating cycle of care. Because the bridge was holy, it was maintained with reverence. Because it was maintained with reverence, it endured, reinforcing its holy status. This spiritual dimension also attracted funding from unexpected sources. While kings and merchants certainly financed bridges, a significant amount of capital came from ordinary people seeking spiritual merit. Donations and bequests in wills were common, with individuals giving money for the construction or repair of a bridge as a pious act to ease their passage into the afterlife. Some religious orders, like the Fratres Pontifices or bridge-building brothers, were even founded with the specific mission of constructing and maintaining bridges, viewing it as a charitable duty to protect travelers. This diverse funding stream meant that money was often available for the best materials and the most skilled labor, not just the minimum required to get the job done. The project was insulated from the cost-cutting pressures that often plague modern infrastructure, allowing builders to prioritize longevity above all else. In Asia, the philosophical underpinnings were different but led to a similar outcome. extraordinary investment in permanence. In China, bridge building was often influenced by feng shui principles and cosmological beliefs. A bridge might be aligned to harmonize with the flow of energy, or kai, between mountains and water, its placement and form calculated to bring balance and prosperity to the surrounding landscape. In Japan, the construction of a major bridge was a communal ritual that could involve Shinto ceremonies to purify the site and appease the spirits of the river. The bridge was seen as a part of a larger, living natural order, and its design sought to integrate with that order rather than dominate it. This philosophical approach encouraged a deep respect for the site and its inherent forces, leading to designs that were inherently more adaptive and resilient to environmental stresses like earthquakes and floods. This cultural and religious context fostered a mindset in the master builder that is almost foreign to our modern, project-based economy. He was not building for a 5-year warranty or a 30-year depreciation schedule. He was building for eternity. He was creating a monument that would carry his name, his guild's reputation, and his community's identity for centuries. Every stone he set, every joint he mortared, was done with the awareness that his work would be judged not by his contemporaries alone, but by 100 generations to come. This profound sense of legacy was a powerful driver of innovation. It encouraged over-engineering not as waste but as wisdom. It motivated the painstaking search for the most durable stone, the most flexible mortar mix, the most stable foundation. Why settle for a good enough arch when, with a little more effort and expense, you could create a great one that would never fall? This stands in stark contrast to much of modern infrastructure development, which often prioritizes low initial cost and rapid construction over long-term durability. We build with an expectation of eventual replacement. Medieval communities built with an expectation of perpetual use. This difference in fundamental intention is written in the stones that remain standing today. The bridges that have survived did so not simply because of clever physics, but because they were loved. They were valued spiritual and civic assets, and this value justified the immense investment required to make them truly, lastingly resilient. The stone arch was not just a structural form. It was a prayer for permanence, a physical manifestation of a society's highest aspirations to create something that would truly endure. It's a fascinating thought experiment to place a medieval master builder alongside a modern seismic engineer in a room together. At first glance, they would seem to speak entirely different languages, one discussing the compressive strength of limestone and the virtues of lead-filled joints, the other running complex computer simulations on reinforced concrete moment frames and the damping coefficients of viscous fluid dampers. Their tools could not be more different, a compass and a chalk tracing floor versus satellite imaging and finite element analysis software. Yet, if they began sketching their solutions for surviving a major earthquake, they would quickly discover that their fundamental principles are astonishingly aligned. Both are deeply concerned with flexibility, the intelligent distribution of mass, and creating an unshakable connection to a stable foundation. The core philosophy is identical. You cannot stop the earth from moving, so you must design a structure that can move with it without falling apart. The most profound divergence between their worlds lies not in the goal, but in the method of achieving it. Modern engineering is fundamentally a practice of prediction. We have developed the ability to model the complex physics of seismic waves, to simulate how different soil types will amplify or dampen those waves, and to calculate precisely how a structure will respond to those forces. We use accelerometers from past earthquakes to create detailed load scenarios and test our designs against them digitally long before ground is ever broken. This predictive power allows for incredible efficiency and optimization. We can design a skyscraper with a precise amount of flexibility, knowing exactly how much it needs to sway to dissipate a specific amount of energy. A medieval builder had none of this. His predictive power was based on lived experience and oral history. He knew his region was prone to tremors because he had felt them or heard his grandfather's stories of the great quake of decades past. His simulations were the real-world collapses of previous structures, and his data set was the collective memory of his guild. His approach was reactive and evolutionary, honed by the brutal, unforgiving audit of nature itself. Yet, for all our advanced technology, modern engineering has often found itself circling back to principles that medieval artisans understood intuitively. Take base isolation, one of the most advanced seismic technologies used today. In buildings like San Francisco's City Hall or hospitals in seismically active zones, the entire structure is separated from its foundation by layers of alternating rubber and steel plates, or massive rubber bearings. During an earthquake, this system allows the ground to lurch violently sideways while the building above floats relatively undisturbed, moving only slightly. This is not a new idea. It is the sophisticated, high-tech evolution of the medieval builder's flexible joint. Those intentional gaps filled with oakum and lead between stone blocks serve the exact same purpose on a different scale, to decouple the structure from the damaging movements of the ground below. We didn't invent the concept of isolation. We simply perfected it with synthetic materials and precise engineering. This return to ancient wisdom is perhaps most evident in the field of retrofitting. When engineers are tasked with protecting priceless historical structures that cannot be rebuilt, they often look to solutions that would be very familiar to a medieval mason. Strengthening foundations with additional concrete or micropiles is a direct parallel to the medieval practice of buttressing and deepening foundations after a quake. Adding steel frames or carbon fiber wraps to reinforce walls is a modern take on the ancient practice of adding external supports or filling spandrels with rubble for added mass and stability. The goal is the same: to add strength and ductility without compromising the historical fabric of the building. In a way, modern engineers are completing a circle, applying their predictive science to preserve structures that were built by observational genius. This comparison leads to a humbling and crucial insight for our time. Our technological prowess sometimes leads us to overcomplicate solutions. We can become enamored with complex active damping systems and smart materials, believing that more technology is always the answer. The enduring legacy of medieval bridges is a powerful reminder that resilience is often born from simplicity, redundancy, and a deep respect for natural forces. Their multi-arch bridges provided multiple, redundant load paths. If one arch was damaged, the others could shoulder the burden. Their use of massive, robust foundations was a form of benevolent over-engineering that prioritized survival above all else. In our pursuit of efficiency and cost-effectiveness, modern design can sometimes sacrifice this redundancy, creating structures that are optimized for specific conditions but fragile in the face of the unexpected. The medieval approach was inherently robust because it was designed for the unknown, for the earthquake that was bigger than any in living memory. Their work stands as a timeless lesson that the most elegant engineering is not always the most complex, but rather the most profoundly in tune with the immutable laws of nature. This intricate dance of trial and error, observation and adaptation didn't happen in isolation. The hard-won knowledge of how to make a bridge withstand an earthquake wasn't the property of a single brilliant mind. It was a collective treasure, safeguarded and passed down through a remarkable institution, the Craft Guild. These weren't just trade unions or social clubs. They were the living libraries and universities of medieval engineering. the critical infrastructure behind the infrastructure. Within the guild halls, the scattered insights of individual masters were gathered, tested, codified, and transmitted to the next generation, ensuring that progress was cumulative, not cyclical, and that catastrophic failures taught lessons that would not be forgotten. The primary engine of this knowledge transfer was the master-apprentice relationship, a years-long immersion that was about far more than learning a trade. A young boy, often as young as 12, would be formally apprenticed to a master builder. For 7 years or more, he wouldn't just be an employee. He would live with the master's family, eating at his table and absorbing the craft not from textbooks, but through relentless hands-on practice. His education began with the most humble tasks, mixing mortars, hauling stone, and learning to care for the master's tools with reverence. This wasn't busy work, it was foundational. By feeling the different textures of sand and lime for mortar, he learned which mixes set quickly for strong joints and which remained slightly pliable to allow for movement. Through this tactile, embodied learning, the principles of seismic resilience were literally ground into his fingertips long before he ever understood the physics behind them. The most critical, nuanced techniques were taught orally and through direct demonstration, a method that preserved subtleties that could never be captured in writing. Imagine a master mason showing his apprentice how to lay stones in alternating courses, a technique known as header and stretcher bonding. He wouldn't just say, "Do it this way." He would explain that by placing some stones with their long side parallel to the wall and others perpendicular, penetrating deep into the core of the pier, they were creating a monolithic, interlocked mass. This wasn't just for looks, it was a crucial defense against seismic shaking, as it prevented the facing stones from simply peeling away from the inner rubble fill during vibration, ensuring the entire pier moved as one solid unit. This kind of tactile wisdom, the why behind the how, was the guild's most guarded secret, but it wasn't all verbal tradition and demonstration. Guilds also maintained incredible repositories of practical knowledge in the form of sketchbooks and model libraries. Master builders would create detailed pattern books filled with drawings of successful arch forms, pier designs, and foundation plans. These were not abstract blueprints but detailed records of what had worked in the real world, annotated with notes on local soil conditions or the size of a flood that a particular design had survived. Some guilds even kept physical models, small-scale wooden frameworks or stone assemblages, that allowed apprentices to see and feel the complex geometry of a ribbed vault or the interlocking joinery of a timber arch. These models were three-dimensional textbooks, making abstract structural principles tangibly clear. This system of preserving proven designs created a powerful feedback loop. A successful bridge in France could inspire a similar solution in England decades later, its form copied from a traveling master's sketchbook, allowing successful innovations to spread slowly but surely across the continent. The guild's role extended beyond education to rigorous quality control, enforcing standards that were literally a matter of life and death. To become a master himself and enter the guild fully, an apprentice had to produce a masterpiece, not a work of art, but a piece of master craftsmanship that was judged by the existing masters. This ensured that only those who had truly internalized the highest standards of the craft could rise to lead projects. This system of peer review maintained an incredibly high baseline of quality. A poorly cut stone or a weak mortar mix wouldn't just be criticized. It could prevent a man from earning his livelihood, creating a powerful incentive for excellence. This collective enforcement of standards is a key reason why medieval bridges display such consistently high craftsmanship, from the smallest village crossing to the grandest capital bridge. The guild ensured that the knowledge of how to build for centuries wasn't lost to corner cutting or short-term thinking. The ultimate testament to the guild system's success is the language of the stones themselves. When we look at a medieval bridge that has survived dozens of earthquakes, we are not looking at the work of a lone genius. We are reading a collective manuscript written over generations. The curve of an arch reflects a form first sketched by a master 50 years prior. The pattern of the stonework embodies a bonding technique perfected through trial and error and then taught to 100 apprentices. The depth of the foundation echoes a guild regulation that mandated digging until reaching solid ground. This was a culture of continuous learning and mentorship, where each generation stood on the shoulders of the last, building higher, stronger, and with more resilience. In an age before patent offices and engineering degrees, the guild was the guardian of resilience, ensuring that the price of past failures was paid only once, and that their lessons were inherited by all who would build the future. This deep, almost intuitive connection to the local environment was the master builder's true North Star, guiding every decision from the quarry to the final capstone. There was no such thing as an off-the-shelf design. Every single bridge was a bespoke solution, a direct and thoughtful response to the unique personality of its place. Before a single foundation trench was dug, these artisans would spend time at the site, observing the flow of the river through the seasons, examining the exposed rock faces on the banks, and speaking with local elders about the history of floods and tremors. They were conducting a pre-modern geological and hydrological survey, gathering the critical data that would determine the life or death of their structure. This profound respect for context meant that a bridge built in the stormy, granite-rich highlands of Scotland would bear little resemblance to one spanning a slow, silt-laden river in the French floodplains, even if they were constructed in the same decade. Their genius lay in this refusal to impose a universal template, instead allowing the landscape itself to dictate the final form. In the rugged, earthquake-prone terrain of mountainous regions, this adaptive thinking led to some of their most ingenious foundation work. Here, the ground was often steep, unstable, and littered with massive boulders. Rather than trying to flatten the entire site, a Herculean task with medieval tools, they embraced the irregularity. They would construct stepped foundations, carefully carving a series of level benches into the bedrock, or building up massive stone platforms that followed the natural contour of the slope. This created a stable, terraced base for the bridge piers that effectively locked the entire structure into the mountainside. It was a way of making the bridge a literal extension of the mountain itself, ensuring that when the earth shook, the two would move as one unified mass, dramatically reducing the differential movement that causes catastrophic failure. The immense weight of the mountain became an ally, anchoring the bridge against the terrifying lateral forces of a seismic event. Conversely, in vast, flat floodplains where the soil was soft and saturated, the primary challenges were instability and scouring. The ground here was like a sponge, capable of turning to liquid under seismic pressure, while seasonal floods could easily wash away any poorly conceived foundation. The medieval solution was twofold: to spread the load and to tame the water. They would construct incredibly wide, raft-like foundations, often using timber grillages, huge crisscrossing lattices of oak beams, that distributed the immense weight of the stone piers over a much larger area of soft ground. This prevented the piers from sinking unevenly, a phenomenon known as differential settlement that could twist an arch and bring the whole bridge down. To combat the erosive power of floodwaters, they extended the approaches of the bridge far back from the main river channel, creating long, gently sloping earthen causeways. This did more than just provide a ramp. It reduced the overall gradient and slope of the bridge itself, making the entire structure lower and more stable. A lower bridge has a lower center of gravity, making it far less top-heavy and much more resistant to the overturning forces of both floods and earthquakes. This site-specific logic reached its zenith in regions known for seismic activity. Here, observation had taught them that long, uninterrupted spans were vulnerable, acting like drumskins that could amplify the vibrational energy of a quake. Their response was a masterclass in pragmatic design. They simply built shorter. Bridges in these zones feature a series of smaller, more numerous arches supported by thicker, more massive piers. While this might seem like a less elegant solution, it is incredibly effective from an engineering standpoint. Shorter spans are stiffer and stronger, less prone to flexing and cracking under the dynamic loads of an earthquake. Those thicker piers, often widened with massive cutwaters, provide a huge amount of inertia and resistance to lateral shifting. The entire structure becomes a robust, repetitive cell-like system where the seismic energy is absorbed and dissipated across many smaller, stronger elements rather than being concentrated on a few large, vulnerable ones. It is the architectural equivalent of a honeycomb, a structure whose strength comes from its modular, interconnected nature. This deeply contextual approach stands in sobering contrast to some of the failures of modern, standardized construction methods. The 20th century, in its drive for efficiency and economy, often embraced a one-size-fits-all mentality, applying the same engineering specifications and material choices across vastly different geographies. This has sometimes led to catastrophic failures when those standardized designs encountered unexpected local conditions, like the soil liquefaction that contributed to the collapse of structures in the 1995 Kobe earthquake. The medieval master builder would never have made that mistake. His entire philosophy was rooted in a humble acknowledgement that the site was the ultimate authority, and that his design had to listen to and learn from the land it would inhabit. This principle of contextual resilience of designing from the ground up, literally and figuratively, is perhaps the most vital lesson these ancient structures hold for our future. It teaches us that true durability isn't found in a universal formula, but in a thoughtful, respectful, and adaptive conversation with the unique demands of a place. Yet for all their robust engineering, these medieval masterpieces were never intended to be brutish or purely utilitarian. They possessed a profound and intentional beauty, a quality that would become one of their most powerful and often overlooked forms of protection. The master builders understood something that modern infrastructure projects sometimes forget. People will fight to save what they love. A bridge that was merely functional might be used, but a bridge that was beautiful, a bridge that lifted the human spirit, that became a symbol of civic pride, that hosted markets and festivals and marriages, would be cherished, defended, and maintained for centuries. This emotional connection, forged in stone and artistry, became a critical component of its resilience, ensuring that when disaster struck, the community's response would be to heal and restore, not to abandon and replace. This fusion of form and function is evident in the smallest of details. Look closely at the stone carvings adorning the parapets of many medieval bridges. While they often depicted saints, mythical beasts, or the coats of arms of local nobility, these weren't just idle decorations. The process of carving these intricate figures required the use of larger, thicker blocks of stone. This added significant mass and weight to the parapet walls, which in turn lowered the bridge's overall center of gravity. A lower center of gravity directly translates to greater stability, making the entire structure less top-heavy and more resistant to the overturning forces of an earthquake or flood. Similarly, the elegant statues that sometimes guard the entrances or crown the central piers are frequently positioned directly above the main load-bearing points. Their weight helps to press down on the arch's keystone, increasing the compressive forces that hold the entire arch in a state of perfect tension, locking the stones together even more securely. The art was literally holding the science together. This principle extended to the very proportions of the bridge itself. The visual harmony that makes a structure like the Pont Vecchio so pleasing to the eye is not an accident of aesthetics. It is the direct result of the geometric ratios that also guarantee its structural integrity. When a bridge looks right, it is often because its arches are perfectly proportioned to distribute weight efficiently. Its piers are adequately sized to resist the thrust, and its roadway is aligned to channel loads smoothly. This visual harmony was a silent language of soundness. It signaled to everyone, from the lowliest farmer to the wealthiest merchant, that this was a solid, trustworthy, and well-built investment. This perception encouraged further investment in its upkeep. A community was far more likely to tax itself for the repair of a magnificent landmark that was the envy of neighboring towns than for a plain, crumbling causeway. The beauty of the bridge became a self-fulfilling prophecy of preservation, attracting the wealth and care needed to ensure its longevity. This emotional investment transformed these structures into the very heart of their communities. They were not just transit points, they were vibrant public squares suspended over water. Their wide decks were crowded with chapels for prayer, shops for commerce, and houses for habitation. They hosted markets, festivals, and public gatherings. They became inseparable from the town's identity. To be from Avignon was to know the Pont Saint Benezet. To be from London was to cross London Bridge. This deep cultural embedding meant that the loss of a bridge was felt not as a mere inconvenience, but as a profound amputation, a tear in the social and economic fabric of the community. This powerful sense of loss guaranteed a powerful response to repair. After a disaster, the call to rebuild was a call to restore civic pride and normalcy. The bridge was family, and you don't replace family, you nurse them back to health. This stands in stark contrast to the fate of many modern, purely functional pieces of infrastructure. A crumbling concrete overpass or a corroded steel truss bridge, no matter how vital to transportation, rarely inspires public passion. Its value is understood intellectually, not felt emotionally. When it is damaged beyond repair, the easiest solution is often demolition and replacement with a newer, more efficient model. The medieval bridge, however, wrapped in layers of art, memory, and identity, defies this disposable logic. Its beauty makes it priceless, its history makes it irreplaceable. This is the ultimate lesson of its aesthetic resilience. We preserve what we cherish, and we cherish what moves us. The medieval builders, in weaving together the practical and the beautiful, the strong and the sublime, ensured that their creations would be loved, and in being loved, they would endure. So what does all this ancient wisdom mean for the engineers of today? Armed with supercomputers and advanced materials, it means that sometimes the most sophisticated solution is to revisit the elegant simplicity of the past. Our modern world is dominated by a philosophy of hyper-efficiency, designing structures to meet precise calculated loads with minimal material, often sourced from across the globe. This approach has given us incredible skylines and vast networks of infrastructure, but it can also create a fragile kind of efficiency, one that leaves little room for error when nature behaves in unexpected ways. The medieval builder, by contrast, operated on a principle of benevolent over-engineering and profound localism. He used stone from the nearest quarry, timber from the surrounding forest, and lime from a local kiln. This wasn't just a lack of logistics, it was a strength. Local materials are inherently acclimated to the local environment. A stone that has weathered the climate for millennia is likely to continue doing so when placed in a bridge. This drastically reduces the carbon footprint of transportation and supports regional economies, but more importantly, it creates structures that are in a deep dialogue with their surroundings. A bridge built from the very landscape it crosses is far more likely to endure that landscape's moods. This medieval pragmatism extends brilliantly to the concept of redundancy. Look at any ancient multi-arch bridge. If a single arch were to be compromised by a flood or an earthquake, the entire structure wouldn't necessarily collapse. The multiple arches provide alternative load paths. The weight of the roadway and whatever is on it can be redistributed to the adjacent arches, allowing the bridge to remain standing, sagging perhaps, but still functional, a lifeline that remains open even in a compromised state. Modern engineering often designs this redundancy out in the name of efficiency, creating structures where a single point of failure can lead to total catastrophe. The medieval approach embraces redundancy not as waste but as resilience. It's the difference between a chain and a net. A chain fails completely if one link breaks. A net can lose several strands and still hold. In an era of increasing climate volatility and unpredictable seismic events, designing more nets and fewer chains is not a step backward. It's a profound step toward a safer, more durable future. Perhaps the most critical lesson is the value of observation. Medieval builders were master naturalists. They learned their craft by watching how trees sway in a storm without breaking, how riverbanks erode and reform, and how animals burrow into stable ground. They understood physics through the intuitive lens of the natural world. Today, we have immense predictive power through computer modeling, but these models are only as good as the data we feed them. They are built on assumptions about the future that are based on the past. But what happens when the past is no longer a reliable guide to the future, as we see with climate change? This is where the medieval mindset becomes vital again. It encourages engineers to get out from behind the screens and into the field, to observe firsthand how water actually flows around a bend in the river, how wind scours certain landscapes, and how local materials age and weather. It's about blending high-tech analysis with low-tech, ground truth wisdom. This isn't to suggest we abandon modern science and start building with rubble and mortar. That would be absurd. The goal is a powerful synthesis to take the timeless principles of flexibility, redundancy, and local adaptation and apply them with all the tools and materials at our disposal. Imagine a modern suspension bridge where the cables are designed with a controlled ability to slacken and retention themselves after a seismic event, mimicking the self-centering stone arch. Or consider using local, low-carbon composite materials in 3D printed structures that are optimized for their specific site conditions, much like a medieval bridge was uniquely tailored to its river. This fusion of old and new could redefine sustainable design, creating infrastructure that isn't just efficient for its design life, but resilient for centuries. The enduring stone arches that still stand today are not just relics, they are a challenge and an invitation. They ask us to build not just for the balance sheet of the present, but for the safety and wonder of generations we will never meet. It's tempting to look at these ancient stone giants and chalk up their survival to simple luck, as if they've been the beneficiaries of a centuries-long roll of the dice with nature. But this notion that medieval builders were merely fortunate is perhaps the most pervasive and misleading myth of all. Their successes were not accidental. They were the direct result of deliberate, calculated choices born from relentless observation and a deep, iterative process of learning from failure. When a bridge stood for 100 years, it was because its builders had likely studied the wreckage of one that fell after 50, identifying the fatal flaw and engineering a specific solution to overcome it. The consistent survival of these structures across different regions and centuries points to a robust, transferable methodology, not a series of happy coincidences. This was a culture that treated every collapse as a lesson and every standing structure as a thesis on resilience, proven in the most unforgiving laboratory imaginable, the real world. Another common misconception paints these master builders as purely instinctual craftsmen, skilled with their hands but devoid of any theoretical understanding. This could not be further from the truth. While they lacked the formal mathematical language of a modern engineer, they possessed a profoundly intuitive grasp of geometry and mechanics. Their compass and straightedge were not mere drawing tools, they were analog computers. When a master set the pivot point for his compass to define the curve of an arch, he was visually solving a complex physics problem, determining a shape that would channel compressive forces along an optimal path. They understood concepts like the center of gravity, lateral thrust, and load distribution not as abstract equations, but as tangible forces they could feel in the heft of a stone and see in the settling of a foundation. Their theory was embedded in their practice, a living knowledge passed down through generations and refined through constant, real-world application. A third, and particularly ironic, myth is the assumption that these bridges are fragile due to their age, that they stand today as weakened relics on the verge of collapse. In many cases, the exact opposite is true. Their incredible longevity is precisely because they were, by our modern standards, dramatically over-designed. Medieval builders did not have the luxury of precise load calculators or the economic pressure to minimize material use for cost savings. Their primary driver was permanence. They used more stone, built thicker piers, dug deeper foundations, and created more massive structures than was strictly necessary for the loads of their time. This benevolent over-engineering created an immense reserve of strength, a huge safety factor that has allowed these bridges to absorb centuries of unforeseen stresses, from the vibrations of modern traffic to seismic events larger than any in recorded local memory. They were built for uncertainties we can now measure but still struggle to anticipate. Debunking these myths is not an exercise in nostalgic romanticism. It is a crucial step toward giving these artisans their proper due. It allows us to see them not as primitive predecessors to modern engineering, but as brilliant innovators working within a different but equally valid paradigm. They were scientists of the tangible, philosophers of force and form, whose laboratory was the construction site and whose proofs were written in stone and mortar. Recognizing the sophisticated relevance of their methods is perhaps more important today than ever before. In an age of complex, hyper-specialized technology and a pressing need for sustainable, durable infrastructure, their principles of using local materials, designing for redundancy, and respecting natural forces offer a powerful and timeless blueprint. Their work challenges our modern obsession with efficiency and reminds us that true resilience is often found in simplicity, robustness, and a deep, respectful dialogue with the environment. This remarkable longevity wasn't just a happy accident of material selection. It was a dynamic partnership between the medieval builders' foresight and nature's own processes of preservation. The very materials they chose possessed an almost magical ability to improve with age, to adapt and even heal themselves in ways we are only beginning to fully appreciate with modern materials science. Take the humble lime mortar binding those massive stones together. Unlike modern Portland cement, which sets through an irreversible hydraulic reaction and becomes brittle, lime mortar sets through a process called carbonation. It slowly absorbs carbon dioxide from the air, gradually reverting back to a form of limestone over decades and even centuries. This isn't a weakness, it's its greatest strength. If a tiny hairline crack forms from seasonal movement or a minor tremor, water seeps in, carrying dissolved calcium carbonate. As the water evaporates, it deposits this mineral, effectively filling the crack and welding it shut. The bridge literally heals its own wounds, maintaining its integrity in a way that rigid, brittle modern concrete simply cannot. The stone itself was a living participant in this process. Over centuries of exposure to sun, wind, and rain, the surface of sandstone or limestone blocks undergoes a fascinating transformation. It develops a hard, protective skin known as a patina, a crust of recrystallized minerals that acts like a suit of armor against further erosion. This natural coating shields the softer stone beneath from the elements, dramatically slowing the rate of decay. The builders intuitively understood this. They often selected stones known to develop a good patina, and they positioned them to work in harmony with the environment. A stone that might weather too quickly if placed in a constantly wet location could be perfectly durable higher up on a dry pier. This nuanced understanding of material behavior in specific microenvironments was a critical, yet often invisible, part of their design genius. Beyond selecting self-improving materials, their designs actively collaborated with the climate to manage water, the arch nemesis of all masonry. Every surface was meticulously shaped to shed water quickly and efficiently. Roadways were gently cambered, arch barrels were carefully pitched, and projecting string courses and drip molds were carved into the stonework. These weren't mere architectural decorations, they were functional hydrological systems. Their purpose was to throw rainwater clear of the vulnerable masonry joints below, preventing constant saturation that could lead to frost damage. In colder climates, this was a matter of survival. When water seeps into porous stone or mortar and then freezes, it expands with tremendous force, a process called frost wedging that can spoil and shatter the hardest rock over time. By designing for rapid runoff, medieval builders were effectively installing a permanent, passive defense system against one of nature's most destructive forces. This meticulous attention to weathering details had a profound, though indirect, impact on seismic resilience. A bridge that is constantly maintaining itself is a bridge whose structural integrity remains uncompromised. Consider the cumulative effect of centuries of frost wedging or water erosion on a modern structure. It slowly weakens the connections, creates points of vulnerability, and reduces the overall cohesion of the build. Now, when an earthquake strikes, it exploits these very points of weakness. A medieval bridge, by contrast, enters a seismic event in a state of peak preservation. Its mortar joints are sound, its stones are protected by their patina, and its drainage systems have kept its core dry for centuries. It faces the violent, unpredictable forces of a tremor as a unified, monolithic mass, not a structure already fraying at the edges. This is why so many have survived quakes that toppled seemingly stronger 20th century constructions. They weren't just strong, they were impeccably maintained by their own design. This long-term perspective is perhaps the most vital lesson for our current era of sustainable construction. We often focus on initial embodied carbon or recycled content, but the medieval approach forces us to consider the entire life cycle with brutal clarity. A bridge that needs to be completely replaced every 100 years, even if built with the greenest modern concrete, will have a far greater environmental impact over 5 centuries than a stone bridge that required only occasional, minimal repairs. Their model was one of radical durability, where the upfront investment in massive, local materials and meticulous craftsmanship paid dividends for generations by drastically reducing the need for replacement, reconstruction, and the consumption of new resources. They built for permanence, creating a legacy of infrastructure that served its purpose beautifully for centuries while leaving the lightest possible long-term footprint on the planet. Perhaps the most compelling proof of their sophisticated engineering mindset comes not from the bridges that have stood untouched, but from those that were dramatically altered. Modern archaeology has peeled back the layers of these structures to reveal a hidden history of continuous adaptation, showing us that medieval resilience wasn't a static quality achieved at construction, but a dynamic process of learning and upgrading. When we examine the stonework of ancient bridges, we often find clear architectural scars, sections where the masonry changes in color, tooling technique, or even the type of stone used. These are not signs of haphazard repair, but rather the fingerprints of deliberate post-earthquake retrofits, proving that these communities were engaged in a relentless pursuit of greater strength long after the builders had moved on. Consider the evidence uncovered at several historic bridges in Italy, sites that felt the tremendous force of the massive earthquake of 1348. Archaeological core samples and ground-penetrating radar have revealed a fascinating response to this disaster. Engineers and masons of the time didn't just patch cracks, they fundamentally reinforced the structures. In multiple cases, they deliberately filled the hollow spandrels, the spaces between the top of the arch and the roadway, with a primitive form of concrete, a mix of rubble and mortar. This wasn't merely dumping trash into a cavity, it was a calculated seismic upgrade. They had observed that the empty, vaulted spaces within the bridge allowed for too much vibrational movement during a tremor. By adding this immense, dense fill, they were dramatically increasing the bridge's overall mass and lowering its center of gravity. This simple yet brilliant modification acted like a counterweight, making the entire structure more stable and resistant to the overturning forces of an earthquake, while the internal friction of the rubble fill helped to dampen destructive oscillations. It was the medieval equivalent of installing a tuned mass damper in a modern skyscraper, but their interventions went far deeper than just filling voids. Excavations around the piers of many old European bridges frequently uncover massive, later additions of stonework, great sloping buttresses, and angled supports that were clearly added after the original construction. These weren't part of the initial aesthetic design, they are structural band-aids on a grand scale. After a quake, if a pier showed signs of shifting or cracking, the solution was to essentially hug it with a new sheath of masonry, broadening its base and locking it more firmly into the riverbed. This effectively increased its resistance to lateral shifting, the primary threat during seismic shaking. In some instances, when scour from floodwaters accompanying the quake had undermined a foundation, they wouldn't just repair it, they would extend it. They'd drive new timber piles in a wider ring around the original base, creating a broader, more stable platform that redistributed the weight over more solid ground. This shows an advanced understanding of soil mechanics. They weren't just fixing the pier, they were fixing the ground it stood on. This ongoing process of enhancement reveals a crucial cultural truth. These bridges were so vital to the economic and social life of a community that their preservation was worth any cost. The investment of time, treasure, and back-breaking labor into these retrofits was enormous. It meant closing a critical transportation link for months, diverting funds from other projects, and mobilizing a skilled workforce. That a community would repeatedly choose to do this, rather than simply building a cheaper, simpler replacement, speaks volumes about the perceived value of the original structure. It was seen as an irreplaceable asset, a masterpiece of craftsmanship that embodied the pride and identity of the town. Each retrofit was an affirmation of faith in the original design, a belief that with a little more reinforcement, this marvel could be made to last another 100 years. This evidence completely shatters the outdated notion of the Middle Ages as a stagnant period devoid of innovation. Instead, we see a culture of continuous improvement where engineering was a living practice. Each earthquake, however devastating, was treated as a full-scale test, providing invaluable data on how structures actually behaved under extreme stress. The master masons who studied the damage were the forensic engineers of their day, and their retrofits were the published papers, written in stone and mortar for all future generations to study. Their work demonstrates that resilience isn't a one-time achievement you check off a list at completion. True resilience is a relentless, ongoing conversation with the forces of nature, a commitment to learn from every disaster and use that knowledge to build back smarter, stronger, and with even deeper respect for the power of the world we inhabit. To truly grasp why medieval builders poured such extraordinary care into making their bridges earthquake-resistant, we must see these structures not just as feats of engineering, but as the very heart and soul of a community. A bridge was far more than a convenient way to cross a river. It was a powerful, multi-layered symbol. It represented safe passage in a world filled with very real physical dangers, connecting isolated villages to the flow of goods, ideas, and people. It stood as a triumphant declaration of human ingenuity, a permanent statement that humanity could not only understand nature's obstacles but could elegantly and permanently overcome them. This profound cultural meaning transformed a construction project into a collective spiritual endeavor, a shared investment in the future that everyone, from the wealthiest merchant to the poorest farmer, had a stake in. This sense of shared destiny meant that funding and building a bridge was rarely the project of a single noble or king. Instead, it was a community-wide effort, often financed through a fascinating patchwork of sources. Taxes and tolls played a part, but so did charitable donations and bequests from wealthy citizens seeking to earn spiritual merit. There are records of entire towns holding fairs and festivals to raise money for a new bridge. This collective investment created a powerful sense of shared ownership and responsibility. When an entire community has literally bought into a project, they demand the highest quality workmanship. There is a built-in accountability. The master builder isn't just working for a distant patron, he is working for his neighbors, his friends, and his own legacy within the town. This social pressure was a powerful quality control mechanism, ensuring that no shortcuts were taken, that the best local materials were used, and that the design was as robust as humanly possible. In regions prone to earthquakes, this symbolic importance was magnified into a matter of sheer survival. After a major tremor, when roads were shattered and buildings lay in ruins, a surviving bridge became the most critical lifeline a community possessed. It was the only route for emergency aid to arrive, for the injured to be evacuated, and for essential supplies to reach the devastated area. Its continued existence could mean the difference between a swift recovery and a prolonged catastrophe. This practical reality elevated the bridge from a symbol of prosperity to a guardian of life itself. The community's identity became intertwined with the bridge's resilience. If the bridge could withstand the earth's fury, then so too could the people. This deep understanding is what justified the immense extra effort, the deeper foundations, the more flexible joints, and the more robust arches. The builders weren't just stacking stones, they were fortifying the very arteries of their society against the worst that nature could unleash. This emotional and practical investment fostered a culture of continuous, vigilant maintenance that is almost unimaginable today. Guilds and local municipalities kept detailed records of repairs, and specific families were sometimes entrusted with the upkeep of a particular arch or pier, their responsibility passed down through generations. The bridge was watched over, cared for, and repaired at the first sign of wear. This proactive stewardship meant that when an earthquake did strike, the bridge was in peak condition, with no hidden weaknesses for the tremors to exploit. Its legendary durability is as much a product of this century's long love and care as it is of the original construction. The bridge was family, and you protect your family. This powerful social contract between a community and its infrastructure is the final, crucial piece of the puzzle, explaining why these stone sentinels have kept their watch for centuries, silently embodying the resilience of the human spirit that built them. What's truly astonishing is that these medieval artisans weren't just building by feel. They were intuitively applying engineering principles so advanced that it would take centuries for modern science to give them names and formulas. They grasped the concept of dynamic damping long before the first vibration sensor was ever invented. Think about the spandrels of a massive stone bridge, those solid walls between the top of the arch and the roadway. Builders didn't leave them hollow, they packed them tight with rubble, loose stone, and mortar. This wasn't just filler, it was a deliberate design choice. During an earthquake, as the entire structure began to vibrate, that chaotic mass of material inside the walls would shift, grind, and settle. This constant internal friction converted the destructive kinetic energy of the shaking into harmless heat and sound, dramatically calming the oscillations. It was a brilliantly simple, completely passive damping system, doing the same job as the massive tuned liquid dampers we install in modern skyscrapers today. Their genius extended into the very physics of load redistribution. A medieval multi-arch bridge is a masterclass in creating redundant load paths. Each arch is structurally independent yet perfectly interdependent with its neighbors. If one arch were severely damaged by a tremor or an impact, the entire structure wouldn't necessarily collapse. The design allowed the adjacent arches to shoulder the burden, redistributing the weight and keeping the bridge standing, perhaps sagging but still functional. This inherent redundancy is a cornerstone of modern seismic design, ensuring there's no single point of failure. They understood that a network of smaller, interconnected elements is far more resilient than one massive, monolithic span. It's the difference between a chain which fails completely if one link breaks and a net which can lose several strands and still hold strong. Perhaps their most elegant innovation was in passive energy dissipation. The arch itself is a natural shock absorber. Its curved form is perfectly designed to translate the vertical force of gravity and the chaotic lateral force of an earthquake into a smooth, compressive thrust that is channeled downward along the curve of the stones into the piers and abutments. The medieval mason, by carefully shaping each wedge-shaped voussoir, was essentially creating a mechanism that wanted to stay together under pressure. During seismic movement, the stones in the arch would minutely shift, the friction between them dissipating energy, and then the incredible compressive force and the precise geometry would encourage them to settle back into their original position. This self-centering behavior is a principle modern engineers strive to achieve with complex and expensive base isolation systems. The medieval version required no synthetic rubber or steel plates, just perfectly cut stone and a deep understanding of geometry. It's a profound thought that these principles, damping, redistribution, and dissipation, were rediscovered and formalized by seismic engineers in the 20th century, only after studying the catastrophic failures of their own more rigid designs. For a time, modern engineering, armed with reinforced concrete and steel, believed it could overpower nature with sheer rigidity. The collapse of many such structures in earthquakes proved this was a fatal miscalculation. The medieval approach was never about overpowering, it was about harmonizing. They worked with the forces of nature, not against them, using flexibility and mass to achieve stability. This realization challenges our linear narrative of technological progress. It shows us that advancement isn't always about inventing something completely new. Sometimes it's about rediscovering the profound wisdom embedded in the past, wisdom born from centuries of careful observation and a respectful dialogue with the natural world. Their intuitive breakthroughs stand as a powerful testament to the human capacity for insight, proving that deep understanding can emerge from the hands and eyes as surely as from a computer model. This global tapestry of seismic ingenuity reveals a remarkable truth. While cultures across the world never communicated, they arrived at eerily similar solutions to the universal threat of earthquakes, each using the materials their environment provided. In China, the magnificent Anji Bridge, completed in the early 7th century, stands as a testament to foresight that feels almost prescient. Its brilliant open spandrel design, featuring two small arches on either side of the main span, wasn't just an aesthetic choice. This innovation dramatically reduced the bridge's overall weight without sacrificing strength, a crucial advantage during seismic shaking. A lighter superstructure possesses less mass, meaning it generates less destructive inertial force when the ground beneath it begins to lurch violently. Furthermore, these openings allowed floodwaters to pass through during the region's notorious seasonal deluges, preventing the entire structure from being swept away. The builders used a series of narrow, slightly curved stone blocks that were interlocked to form the main arch, creating a structure that could absorb and distribute stress with incredible efficiency. It's a design so advanced that it remained the world's longest open spandrel arch bridge for over 1,000 years, a silent guardian that has weathered dozens of major earthquakes thanks to a principle modern engineers call weight optimization. Journeying to the arid landscapes of ancient Persia, we find a completely different philosophy embodied in their formidable fortified bridges. Here, the primary building material was often baked brick, bound with a mortar made from sand, clay, and gypsum. While strong in compression, brick arches generate immense lateral thrust, a dangerous force during an earthquake. The Persian solution was one of breathtaking mass and monumental stability, the construction of colossal, fortified abutments. These were not simple riverbank supports. They were often integrated into the gateways of cities or the walls of fortresses, massive structures that could weigh thousands of tons. Their incredible weight and broad base acted as a counterbalance to the thrust of the arches, anchoring the entire bridge firmly to the earth. During a tremor, while a lighter, more flexible bridge might sway, these Persian giants were designed to simply not move at all, their immense mass and deep foundations making them virtually immovable objects in the face of the Earth's energy. It was a strategy of overwhelming stability, a stark contrast to the flexible approach seen elsewhere, yet perfectly suited to their materials and the seismic character of the region. Perhaps the most astonishing contrast in design philosophy is found in the Andes Mountains of Peru, where the Inca civilization mastered the art of suspension bridges using a material that seems impossibly delicate, woven grass. The Cutwaters Bridge, rebuilt annually in a tradition that continues to this day, is a masterpiece of organic engineering. The Incas used iku grass, twisted into thick cables, to create a suspended roadway that could span breathtaking gorges. In an earthquake, this design was unparalleled. Unlike rigid stone, which can crack under differential movement, the flexible grass cables allowed the bridge to swing and sway with the seismic waves. The entire structure acted like a shock absorber, moving with the energy of the quake rather than resisting it. The cables were anchored to massive stone abutments on either side of the canyon, but the system's genius was in its dynamic response. This annual rebuilding ritual was not a sign of fragility. but a sophisticated form of planned renewal and community engagement that ensured the knowledge of its construction was never lost and the materials were always at their strongest. It represents a living dialogue with seismic forces, where resilience is found in yielding and adaptation, a philosophy woven literally into every fiber of the bridge. Meanwhile, back in Europe, the strategy leaned heavily on the compressive strength of stone and the principle of vaulting. Builders created incredibly robust, multi-arch structures where the weight of the vault itself became its greatest asset. The sheer mass of these stone bridges lowered their center of gravity, making them extremely resistant to overturning. The multiple arches created a repetitive, cell-like structure where seismic energy could be dissipated across many similar elements. The Romans had perfected the semicircular arch, but medieval European builders refined it, sometimes leaning towards the slightly pointed Gothic form, and often varying the span and pier thickness based on the riverbed below. This created a structure that was not perfectly uniform, but perfectly balanced for its specific site. The rigidity of the stone vault was not a weakness but a calculated defense, ensuring the bridge moved as a single, monolithic unit during a quake, with the solid spandrel walls filled with rubble acting as a damping mass to quiet the vibrations. This diversity of approaches, from China's weight-saving ingenuity and Persia's monumental mass to the Inca's flexible fibers and Europe's rigid vaults, paints a picture of a planet full of innovative minds all converging on a single goal: to build connections that would not break, no matter how violently the earth trembled beneath them. Looking ahead, the enduring legacy of these medieval bridges offers a powerful blueprint for the future of construction, especially as we confront an era defined by climate volatility and increasing seismic risks. Their design philosophy, centered on working in harmony with nature rather than against it, resonates deeply with the core principles of modern green engineering and sustainable development. These ancient builders understood that resilience wasn't just about brute strength. It was about adaptability, about using local materials to minimize environmental impact, and about creating structures that could evolve and endure over centuries. This mindset is incredibly relevant today, as we seek to build infrastructure that can withstand not only the earthquakes of today, but also the unpredictable challenges of a changing climate, from intensified flooding to soil instability. Imagine the possibilities if we began to merge this historical wisdom with our contemporary technological capabilities. We now have advanced materials like carbon fiber composites and self-healing concrete, along with sophisticated modeling software that can simulate stresses with incredible precision. But what if we applied these tools to emulate the time-tested strategies of the past? We could design buildings with base isolation systems that are inspired by the flexible joints of medieval stonework, or use 3D printing to create structures with the optimized, site-specific geometries that master builders once laid out with chalk and string. We might develop new composite materials that mimic the way traditional lime mortar allows for micro-movements and self-repair, combining ancient chemical principles with modern nanotechnology. This isn't about nostalgia, it's about creating a powerful synergy between the best of both worlds: the intuitive, holistic understanding of the past and the predictive, analytical power of the present. This approach could fundamentally redefine the next era of construction, shifting our priorities from short-term efficiency and cost-saving to long-term durability and elegance. For decades, much of our infrastructure has been built with a focus on initial budget and rapid completion, often leading to structures that require constant maintenance, frequent repairs, or complete replacement within a few decades. The medieval model invites us to adopt a more expansive view of value, one that accounts for the entire life cycle of a building or bridge, a structure that lasts for centuries, requiring only minimal upkeep, ultimately has a far lower environmental impact and economic cost than one that needs to be rebuilt every 50 years, even if the initial investment is higher. This long-term perspective encourages us to invest in quality, to choose materials that age gracefully, and to design for adaptability so that structures can be easily modified or reinforced as needs and conditions change. The result could be a new architectural language that seamlessly blends durability with beauty, where resilience is woven into the very fabric of our cities in ways that are both functional and inspiring. We might see bridges that are not only capable of withstanding earthquakes but also serve as vibrant public spaces, adorned with green infrastructure that manages stormwater and supports local ecosystems. Buildings could be designed to passively regulate temperature using ancient principles of thermal mass and natural ventilation, reducing their reliance on energy-intensive systems. This vision of the future is not about going backward to a simpler time. It's about moving forward with a deeper wisdom, one that recognizes that the most sustainable and resilient solutions are often those that have been proven by the ultimate test of time. By learning from the past, we can build a future that is not only safer and more resilient but also more beautiful, more connected to our environment, and more worthy of lasting for generations to come. These stone sentinels from the 13th century do more than simply span rivers. They bridge time itself, connecting our modern search for resilience with an age of profound practical wisdom. Their enduring presence is a powerful testament to a forgotten truth. That true strength is not about dominating nature with overwhelming force, but about engaging in a thoughtful dialogue with its immutable laws. These builders achieved what we so often struggle with today, a perfect, elegant balance between unyielding strength and graceful flexibility, between raw functionality and soul-stirring beauty. They prove that the most durable solutions are not born from complex formulas alone, but from a deep, observant relationship with the material world, a philosophy where every stone, every joint, and every curve is a conscious response to the environment it inhabits. This legacy offers us a crucial way forward. In an era of accelerating climate change and unpredictable seismic activity, we are confronted with the limitations of our own disposable infrastructure and short-term thinking. The medieval model presents a compelling alternative, a call to build for the long now. It challenges us to shift our priorities from mere efficiency and initial cost to embodied longevity and adaptive resilience. Imagine the profound impact if we applied this centuries-minded perspective to our modern projects, designing bridges, buildings, and cities not for decades but for centuries of service. This wouldn't be a step backward but a great leap forward, a fusion of timeless principles with cutting-edge technology, where self-healing materials mimic traditional lime mortar and advanced sensors monitor stress in structures designed with the innate wisdom of a multi-arch span. Ultimately, these ancient crossings stand as silent mentors, their stones holding lessons more relevant than ever. They remind us that ingenuity flourishes under constraint, that observation is the most powerful tool, and that the most sustainable path is often the one already paved by nature. Let these monuments inspire a new generation of builders, engineers, and dreamers to embrace this richer, more responsible ethos. Let's carry their legacy forward not through replication, but through inspiration, by building a world that is not only safe and functional, but also enduring, beautiful, and deeply respectful of the forces that shape our planet. Let's build for the future by learning from a past that still stands strong.